Okay, recording's rolling. Oh, share my screen. So, and we're ready to start. I didn't print these out for you guys, but you can access these questions on Google Classroom. So they're there if you wanted. After a cannonball is fired into frictionless space, the amount of force required to keep it going is equal to? Yeah, 0 newtons. Hey, isn't that the law of inertia? Newton's first law of motion? Isn't that the same as the Voyager spacecraft? Or remember we were doing free body diagrams? That rocket was moving at constant velocity, but it didn't need to have its engines on. Right? Just inertia. That's the only thing keeping it going. Inertia. We got Danielle, Ian, Caitlin, Kira, and Gabby. If the force of gravity suddenly stopped acting on the planet, what would they do? Oh, not here. Hello, Mr. Griffin. Yep, I'm sending it down. All right, Freddie, send you for checkout. They send you down there. Destination, attendance. All right, what we're doing here. They were moving straight lines tangent to the orbits. Now this one I want to draw up for you guys. Have a good weekend. Right, so suppose we got here a star, like a sun, and a planet. So star, planet, and planet's going around. Okay. This path is actually elliptical, not quite circular. We'll talk about that in the future. Which actually launched investigation in physics in the first place, hundreds of years ago. But this planet's going around. What's keeping it in orbit is a gravitational force. There's a force from the star pulling in the planet. There's also a force back the other way too. The planet's also pulling on the star. But which force is bigger? Same force. Still can't trick you guys. And at this exact moment, the planet happens to be moving in this direction, but like this velocity type, right? Isn't the planet always moving tangent to the to this orbit, tangent to the orbit? If you turn gravity off, say right here, turn gravity off, that's the way it would go. It would fly off that direction. That's Newton's first law of motion, law of inertia. You know what this is also the answer to? Is if you put a ball on a string and you start wheeling it around, zoom, 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 and you cut the string, does that ball fly straight away from you? No, the ball is going to go tangent to its path. Yeah, tangent to its path. That's the law of inertia, first law of motion. Back to Cahoots. Yeah. Oh, Ian to the top spot. Danielle, Kira, Caitlin, Cotter. A 30 Newton force and a 40 Newton force act in opposite directions. What is the net force on that object? Hello, Mr. Griffin. Yep, send him down. Right, Andrew, have a good weekend. Okay. Come on. Mouse. And then check out. All right. Oh, yeah, you guys got it. So connected tip to tail, 30 one way, 40 the other way. You see the net force would be 10 newtons. All right, you guys got that. Okay. You got Danielle to the top. Ian, Kira's on fire. Sydney, Caitlin. Equilibrium. Those are all true statements. So the net force is 0. The blue and yellow answers just say the net force is also 0 along any particular axis, along the x-axis, y-axis, z-axis, something like that. Now, later on in this class, we'll actually add another condition to equilibrium. We're going to say that the net torque also zeroes out. Torque is the idea of anytime you open a door. You guys ever wondered why the doorknob is opposite of the hinges? What if it was really close? Would it be really hard to open the door? Yeah. So torque has to do with not only the force you push with, but also like a lever arm. So that's later, but kind of a sneak peek ahead. And I'll also bring that up because that's sort of related to this next question. This question. who's green person? Weighs 600 newtons. What is the tension in each of those strands of rope? I see 2 brown strands of rope. He's hanging right in the middle, right? He's hanging right in the middle. Yeah. So each strand of rope is pulling up with 300 newtons force. 300 plus 300, doesn't that balance out the 600 newtons down? Okay, that's how that works. Now, the fact that he was hanging right at the middle, well, maybe that said, okay, the weight has to be divvied, half and half. Right? But what if he wasn't hanging right at the middle? What if he was hanging like 3/4 over to the side? Do you think that the rope he's hanging closer to, actually the tension goes up a bit? Right? But do you think that the 2 ropes still add up to 600 newtons no matter what? That's also true, right? But all those statements are true. Okay? You know what? Side story here, but this is a fun side story. Paul Hewitt, college guy. Paul Hewitt. He actually he worked odd jobs for a long time. He got a late start in life. He never went to college until he was I think it's 26 or 28, something like that. And different jobs he's working. He was a boxer at one point. People punched him in the head. True story. And one point he worked as a sign painter. He painted signs. He was on the scaffolding, and the scaffolding was being held up by ropes, right? Just like that last picture, sort of. Well, it's probably not hanging from below, but he was working with another sign painter. And they would exchange questions back and forth, like, wonder if we walk closer to this side, I bet the tension in this rope is increasing. But they couldn't figure out exactly how to quantify that or exactly how to say it, other than that was probably the case. But they would ask each other lots of physics and philosophy questions that they didn't know the answer to. So finally one day, Paul, he was like, hey, I'm going to go back to college. I'm going to learn this. So yeah, that question in a way led to an influence on this classroom. Ooh, Danielle, on fire. Got Ian, Caitlin, Kira, Vincent. Friction is a force that always acts. Yeah, opposite of the object's motion. Like if we're talking about kinetic friction, right? So opposite of the motion, 2 surfaces are sliding past each other. Danielle, Ian, Kira, Vincent, Sydney. Which has more mass, a kilogram of feathers or a kilogram of iron? Oh, what's up that Kahoot music? Yeah, same mass, right? They're each 1 kilogram. They have the same inertia. They also have same weight, same surface of the planet. They have different densities. They have different volumes, but same mass, same inertia. Ian, on fire. How much does a 3 kilogram bag of bolts weigh? What is its weight? All right, so to go from mass to weight, because this is a mass number, right? 3 kilograms, that's mass. That's how much matter, how much inertia. To go to weight, don't you have to do mass times gravity? And at the surface of Earth, isn't gravity pretty close to 10 meters per second squared? So what is 3 kilograms times 10 meters per second squared? That would be 30 newtons. Now, if you use 9.8 instead of 10, then you got a little bit short of 30 newtons. Okay? So about 30 newtons. You got, same liters. All right. The acceleration produced by a net force. Yeah, those are all true statements. It's directly proportional to the magnitude of the net force. So more force, more acceleration. Right? If you triple the force, you triple the acceleration. Right? But it's also inversely proportional to the mass of the object that the force is acting on. Right? Isn't this Newton's second law of motion? Acceleration is net force divided by mass. And of course, acceleration is also in the same direction as the net force. Those are all true statements. Yeah. Right. Caitlin, hopping on the top 5. Ian's still in the lead. When an object reaches terminal velocity, its acceleration is now zero meters per second squared. So terminal velocity. Now you do need, say, like air drag to go to be incorporated to reach something like this. So when the air drag builds up to the same as the weight of the object, those 2 forces balance out. Equilibrium, right? Goes down at constant speed, called terminal velocity. Same leaders. Ian still keeping the lead. A bowling ball weighs 20 newtons when it is held at rest in your hands. What is the net force? Net force at rest. 0 newtons. Right? So if you drew a free body diagram for this, would it be 20 newtons acting down is the weight, but also 20 newtons from your hands holding it up. That would let it be at rest. So at rest, isn't that one example of equilibrium? So all the forces better balance, right? Yeah, so 0 newtons net force. Everything is just sitting there at rest. Ooh, Sydney, to the top spot, on fire. Ian and Danielle, top 3. Apple weighs 1 newton. What is the net force on the apple when it is in free fall? Yeah, ignore air drag. Free fall. Yeah, it is 1 newton because that's the weight of the apple. The weight of the apple is 1 newton. And if it's falling, say when Newton was watching the apple fall off the tree, then yeah, anything that's under the influence of only its own weight, that's what free fall is. Right? Hey, what is the mass of that apple? Can anybody estimate what the mass of that apple is approximately? So before this we went from mass to weight by multiplying by 10 meters per second squared. Yeah, what do you think, Alicia? 100 grams, exactly. Yeah, you guys hear Alicia? She says 100 grams, because that's also 0.1 kilograms, right? Take 1 newton, divide by 10 meters per second squared. Yeah, 0.1 kilograms or 100 grams. Good call. Posted. Ian, Sydney, Danielle, Vincent, and Kira. Girl pulls on a 6 kilogram wagon with 18 newtons of force. What is the acceleration? Yeah, 3 meters per second squared. So 18 newtons of force acting on 6 kilogram wagon results in 3 meters per second squared. That's the rate that the wagon is speeding up. Ooh, Sydney, back to the top. Oh, pressure. I haven't told you guys about this yet. You guys need this. Pressure. Oh, you guys did get it. Yeah, force per area. Now, after this Kahoot finishes, I'm going to tell you guys a bit more about pressure. So I'll talk about a little bit about it right now. So when you guys are pumping up your bike tires, you guys buy an American pump, and you guys are like looking at the needle moving on that American pump. Right. What unit does it read on the pump you could buy from the store here for pressure? Yes. PSI. Exactly. Yeah, you guys hear voting? It says PSI. And what does PSI stand for? What per what? Pounds per. What is SI? Square inch, right? Pounds per square inch. Hey, pounds, is that like a force? Square inch is like an area, right? That's exactly what that is, isn't it? Right? Now, in this class, we almost exclusively use the metric system. So what do you think the unit would be in this class for pressure? Force is measured in newtons. Area can be in like square meters, right? Square meters. Hey, could that be Newton per square meter? Right. I'll tell you what, too. Newton per square meter also has its own name. It's called 1 Pascal. Right? Yeah, that's going to come back. I'll tell you guys more about that after the Kahoot. Because you actually need pressure a little bit to explain that mystery cup that we're going to get to. You're on a frozen pond. The ice starts to crack. Oh, no. You lie down and begin to crawl. What does that do? Yeah, decrease the pressure on the ice. Because remember, so you can't change the force because your force would be represented by your weight, and that's not going to change. Right? But you can change how your weight is distributed, right? And so, right, you can spread that out. Do you guys know what snowshoes are? Snowshoes? Here we go. Right. So, say you live up in Alaska and it just like dumps massive amounts of snow, and you're like, how am I going to walk around this town? You throw on these snowshoes. If there's like couple meters of snow on the ground, you can actually walk on top of the snow. Now, of course, you can't change your force down on the snow, can't change your weight, but you can distribute it differently. So you wear these big old shoes, it spreads out your weight, you can actually walk right across the top of the snow. Yeah, that is snowshoes. Decrease the pressure. Ooh, Kira's on fire. We've got Vincent, Danielle, Ian, and Sydney. 17 Newton falling object encounters 9 newtons of air resistance. What is the net force? Yeah, 8 newtons of net force, right? So just subtract the two, right? 17 down, 9 newtons of air resistance up. The difference would be 8 newtons, right? Net force. Okay. hey, isn't 8 newtons, isn't that pretty close to half of the actual weight of the object? Sure, is it right? So if you took that 8 Newton net force and you divided by the mass of the object, by the way, what would the mass of this object be pretty close to? How many kilograms is that about? Yeah, like 1.7 kilograms, right? Right, 1.7? Yeah, somewhere there. Yeah, the logarithmic difference. Yeah, 1.7 kilograms. I bet if you took 8 newtons and divided by 1.7 kilograms, you probably get pretty close to about 5 meters per second squared, about half of the free fall rate. Okay, that makes sense. Half the net flow. All right, we've got Sydney still leading. Ian's on fire. A bat imparts a force on a ball. What is the reaction force? So bat on ball. Reaction is everybody got it. Ball on bat. Bat hits the ball. Ball goes against the bat. Okay. But which force is bigger? Bat hitting the ball or ball hitting the bat? They're the same. I still can't trick you guys. Someday I would trick you. Yeah, same force. Isn't that Newton's third law of motion? For every force, there's an equal and opposite reactive force. Okay. Now, of course, the effects are different. One reason is that the bat is more massive. The other reason is that the bat's being held in the hands of a player who has his feet planted into the ground. There's friction going on there. So, yeah, the changes in motion of those two objects is completely different. But the force interaction is the same both ways. Okay. Bat on ball, ball on bat, same force. Got an unfortunate bug splatters against the windshield of a moving car. Compared to the force of the car on the bug, the force of the bug on the car is the same. Still can't trick you guys. Yeah, same force. Really, same force. Splat. Huh. How about this? Let's go to the same premise, same story. Unfortunate bug splatters against windshield of a moving car. Compared to the rate change motion of the car, the rate change motion of the bug is much larger, right? Think about it. Have you guys ever been driving, say up the interstate, and a bug goes against the windshield of your car? The motion of the car, does that really change? Maybe like imperceptibly, maybe like to a negligible amount. You barely notice like driving. Maybe you might notice if you ran into like a million bugs. It's like maybe that might slow down the car a little bit. But one bug, yeah, you would hardly even notice. But from the bug's point of view, doesn't it undergo wildly different change of motion? Like maybe it was just hovering, like, yeah, what a nice, beautiful sunny day, and then suddenly it's moving 70 miles an hour, right, in like an instant. Yeah. So now the car and the bug, they have wildly different masses, right? Doesn't the car have a huge amount of mass? The bug has a tiny amount of mass. So the forces are the same, the force interaction, but the accelerations are different because the masses are different. I got Sydney, Ian, Kira on fire. Last question. 2 people pull the rope, tug of war. Each pulls with 600 newtons of force. What is the tension in the rope? A challenge question. Yeah, somebody didn't get that. Yeah, 600 newtons. Good call if you got that. After we see who gets the Kahoot medals, I'll switch over and I'll draw a 3-body diagram for you guys for this. Right, to the winner podium with the bronze, Kira. With the silver, Ian. And the gold goes to Sydney. All right. Oh, who are our runners up? We got Danielle and Caitlin. Yeah, nice job, guys. Nice job. That's gonna flip my screen over here. I need to draw you guys a 3-body diagram for that tug of war scenario. So here's our agenda. Did I tell you guys double check focus, make sure you got everything in? I do want to get you guys your quizzes back pretty soon, but I'm still waiting for a few more to come in. So as soon as I get those back to you, then you can handwrite solutions and go back for partial credit. But gotta do that first. The Kahoot Newton's laws, and we gotta finish this up, and then we'll get to this puzzle cut. See if you guys figured this out. But I need a 3-body diagram for 2 people playing tug of war. So here's this guy, rope, this guy. and they're both tugging on this rope. Okay? Now they've got their feet planted into the ground. That means they're allowed to stay in place as they're pulling. So that's part of the story. But let's just look at individual points. Let's say a point near where this guy's holding, a point near where this guy's holding. So the guy on the left is pulling to the left with 600 newtons of force, okay? And the guy on the right is pulling back with also 600 newtons of force. Now, I'm not drawing the whole story, like the friction between their feet and the ground and all that, but you guys get to see this partial story. Makes sense, right? Okay. Now, that rope is being held in equilibrium because it's not moving. It's probably just kind of stationary. Okay? Hey, it's kind of like the monkeys with the pulling on the vines with the bananas, right? Like, just kind of pulls back. Let's look at it in an individual point, like an individual segment of rope. Maybe like that point right there. Well, if it's in equilibrium, isn't the rope pulling back the other way with 600 newtons of force, right? And then same story with this point, this individual point. If you took a little tiny segment of rope, like a few fibers or something, 600 newtons both ways, that would put it into equilibrium, wouldn't it? Right? And these 600 newtons represent the tension in the rope. The tension is 600 newtons. Right? Or if you don't like that explanation, sometimes what I think is helpful is to replace this guy with a tree. Now this guy's playing tug of war against a tree. Who's going to win? Who's going to win? And he's still pulling back with 600 newtons of force. The rope better be pulling back with also the tension of 600 newtons. Okay. And hey, replacing this guy with a tree, from a physics point of view, did anything really change? Not really. From a biology point of view, but not a physics point of view. It's still 600 newtons, 600 newtons. Like that. Maybe if that helps at all. So there you go. Here's a partial free body diagram anyway for that last question. Okay. All right, you guys ready for Pythagoras cup? Oh, that's what this is called, by the way. It's called a Pythagoras cup. I didn't want to tell you guys that because I didn't want you to just Google the answer, but take you guys through the story again. So the story went like, draw a cross section. Right? So take a look at this cup. You guys see a straw hole at the bottom. Flip it over. See it's some kind of straw hole there. That's interesting. If I saw this in half, like, then cross section might look like something to do like this. Where here's a straw hole there, straw hole here. And how was the straw connected inside this thing? How's the straw connected inside so that the following happens? What you guys saw on Monday. What you guys saw on Monday was that I filled this cup halfway with water, and the water stayed in the cup, no problem, perfectly good cup. Then you fill it all the way to the brim, and now the water starts draining out the bottom. And there's one last twist though, which is that when the water level falls down back to halfway, which it was perfectly fine before, it was stable. Right? It no longer is. It just keeps going, keeps draining, and until the entire cup is drained. Called a Pythagoras cup. Hey, that's the triangle guy. Also called a greedy cup. The idea was if you had guests over at a party and he filled it up like halfway with wine, like, give me more wine. He's like, yeah, certainly. He fills it up and like, oh no, I'm covered in wine. So did anybody figure out in the last few days, or have a pretty good guess, how are these straws connected? I mean, what's the straw doing on the inside? Wait,
You're going up and then back down?
Oh, yeah, you were gonna say the same thing? All right, Karen and Sydney are both saying, they got it, right? Exactly, yeah. All you do is wrap a straw up the side of the cup, yeah. And I'll show you guys why that works. Take you guys through the story again. The straw's doing something like this. So remember, the first time you fill it to the halfway line, what happens is that, some of the water goes into the straw, but only up to that point. Oh yeah, it totally does stay in there, doesn't it? So, okay, so we're okay so far. Stays in. But if you fill it to the brim, then doesn't this entire straw become flooded with water? Right? So it's going to drain out the bottom. That's the lowest point, just like water wants to flow downhill. Same story. Then that very final twist, the water level goes back to halfway again. Now, at this point, there's been a state change. And that's that the straw is still flooded with water. So it's still one continuous mass, and the water gets siphoned out the bottom. It all gets siphoned out the bottom. The entire cup drains. Okay. Now, I did mention that this does have something to do with pressure. Did I just give you guys some pressure notes? Here. So pressure is force per unit area. Okay. And the commonly used American type unit, which actually comes from Britain, is pounds per square inch. So pounds per square inch, or called PSI, for the units. Okay. But in this class, we're using metric system. So wouldn't that be force per square, Newton per square meter? Okay. Newton per square meter. Okay. That's called 1 Pascal. So PA is Pascal. Okay. And I'll tell you guys what that is. You guys see this 100-gram lab weight that, remember Alicia earlier said 100 grams that weighs approximately 1 Newton? It's like 0.98 Newton, so we'll call it 1 Newton. Okay, so 1 Newton, that's that. 1 square meter, you guys see the tiles on the floor? Okay. What if you rope off 3 by 3? So you make like 9 tiles, 3 by 3. Isn't that pretty close to a square meter? Not exactly, but pretty close. Okay. So if you had a big old foam board that was basically like 1 square meter, 1 meter by 1 meter, and you stack this right on top of it, like it's force pushing down on it, that would represent 1 Pascal worth of pressure. Like 1 Pascal. That's what 1 Pascal is. Now, we are in a giant atmosphere that is many pascals. Wonder if you guys can figure out, does anybody know 1 atmosphere? There are multiple ways to quantify pressure. One way is in atmospheres. Another way is in PSI. Another way is in pascals. Does anybody know what 1 atmosphere is equivalent to? Go ahead and tell you guys. It ends up being 14.7 pounds per square inch, which is also called 101,000 pascals. Woo! That's a big pressure, isn't it? And the reason I'm bringing this all up with this Pythagoras cup is because this cup would not work in a vacuum. I'll tell you guys why in a minute, but let's think about how to wrap our brains around this. How huge is this number? Like, we are in 1 atmosphere of pressure right now, but how much is that? Guys, how much does a bowling ball weigh about? Maybe about 10, 15 pounds, something like that, 10, 15 pounds. Hey, pounds per square inch, right? Pounds per square inch. What if you had like a bowling ball on every single square inch of your skin? What would that feel like? Well, I'll tell you guys, you're feeling it right now, because that's what 1 atmosphere of pressure is. It's like you have a bowling ball on every single square inch of your skin. I mean, you would definitely notice if it was gone, right? If you walk into a void like a vacuum chamber. Right? So it's also equivalent to this. That's a crazy amount of pressure, isn't it? Right? Here's another way to quantify atmospheric pressure. Sometimes it's measured in like depth of water, or sometimes depth of mercury. Look at some old original barometers. Okay. But suppose you and your friends are standing out by the pool. You're standing out by the deep end. You're looking down to the deep end. Woo! That is a deep pool down there. You guys see this really deep pool? You're looking down to the water. It's like the get shallower on the side, something like this. You're looking down into the water. How far down deep would you have to dive to effectively double the pressure on you? Like if you're at 1 atmosphere of pressure up here at the surface because of the actual atmosphere. How deep down into the water we have to go before you feel 2 atmospheres of pressure? Does anybody know? It's about 10.3 meters. Right? At 10.3 meters, then you would get to 2 atmospheres. So here's 1 atmosphere of pressure. Here's 2 atmosphere of pressures down here. 10.3 meters. Okay? Let's go back to this cup, and I want to tell you guys why this cup needs to be in an atmosphere to work. Okay? So would this work in a vacuum? Right? Well, first of all, water actually boils in a vacuum. That's kind of a side story to this. 2 things cause boiling, like a state change from liquid to gas. One is an increased temperature. The other is a decreased pressure. So like this vial right here, this actually isn't water, it's ethanol, but so that's part of what makes this work. But if this is a partial vacuum, it's easier to make it boil. So that aside, we'll talk about that in the future. Let's suppose there's just some liquid that exists in the vacuum, which could be. Why would this not work? Well, because when we fill this to the brim, it starts to drain, all fine and good. When it gets back to the halfway level mark, this actually wants to split and open up a void here, which it would if this whole thing were in a vacuum. It would just split left, right, and then the liquid actually would stagnate at the halfway mark. But because this is in a huge pressure, I mean, this is a huge pressure, isn't it? Right? This water can't split. It has to stay as 1 continuous mass, and that's why the entire mass of water gets siphoned out, because it has to stay as 1 continuous mass. Right. How about this? Let's suppose you want to build a very large Pythagoras cup. Suppose, let's make a roadside attraction, like the world's largest Pythagoras cup. We're going to build one of these, make it out by I-95, get more tourists in Florida. What is the maximum height that this would actually work? Because Earth's atmosphere is finite, so I bet there's a finite height that this would actually continue to work. Can anybody tell me what is the maximum height that this might theoretically be able to go to? Before, at the top, it would be a vacuum, and it would just split anyway, and the water would just stagnate, and it would no longer be a functioning Pythagoras cup. 10.3 meters. Yep. You can't build it any higher than that. That's the longest straw you could use. If people first figured this out when pumps were invented. Suppose there's a town at the top of a hill, little town up here, okay. And we need water. Oh, hey, there's a lake down here. Okay, so we'll walk down the hill every day. We'll fill pails with water, truck them back up. Oh man, this is really laborious. And then pumps are invented. We're like, oh, hey, we can just put a pipe down here and just start pumping up the water. Towns all over the place start doing this. But towns on really tall hills realize you can't pump more than 10.3 meters because at that point, the pressure decreases all the way to a vacuum. The water boils at the top, and you just can't pump it beyond that. So that's a island. That's the theoretical longest straw you could use. You can only, something like that. All right. Just.
So are you saying if we take a pipe and we put it 10.3 meters upwards, fill an entire thing with water at the top, the water would be boiling?
It would be. If you have like a tube, you take a tube, you put it underneath the water and like pull it up like this, and you have a tube, and you just keep drawing up water, it would only go up to 10.3 meters. And then, at the top it would be a vacuum. In perfect vacuum, at room temperature, water actually boils. Yeah.
How tall is the school?
I forgot that. So you guys think about that. That's a good question. You guys have a good weekend.